Welcome to lesson 5, video 2. Let's start off with a slight diversion. That's about the body temperatures that we have. This is supposed to look like a thermometer, but since I can't put anything in my mouth because of the virus, I was not able to put that. But some research shows that you're not as hot as you think. That is, there is this study that they did at Stanford that when they found the 98.6, a lot of people had tuberculosis and some other diseases, so the average went up. Actually, it may be that in our industrial age, the average temperature might be about 98 or 97.5, and it seems to be decreasing by about 0.03 degrees centigrade per birth decade. I don't know what to do with that, but maybe that will help you with your health. All right, so today we're still answering this question: what predictors do we include in our model? And in video 1, we set up the null hypothesis where we had it verbally. We had an original model where we had k predictors, and then we said, okay, maybe the last few predictors do not help explain the response why, perhaps after we did some exploratory analysis, or we said the model is the reduced model. We don't need that dead weight or the coefficient version saying that all those betas are 0, or at least in the alternative hypothesis, at least one of them is non-zero. The partial F test is given by this. Looks a little scary, but if you have it written down, you can find the data pretty quickly on the output, either from Excel or from Minitab. However, you do need to do it by hand. Just one note, this kind of helped me because my instincts were not always correct when I first started this, but the sum of squares errors reduced is always bigger than the sum of squares errors of full. That means if you take the sum of squared errors reduced minus the sum of squares errors full, that'll always be greater than or equal to 0. The idea is that the more predictors you include, r squared goes up. And as the rain goes up, the sum of squares residuals go up. As the r squared goes up, the sum of squares residuals go down. In other words, sum of squared errors will get smaller going from reduced to full. Let's go it the other way. Likewise, if you take away predictors, r squared will go down, and then the sum of squared errors will go up. So in other words, if you start with full and take away predictors, then the reduced should have a higher sum of square error. In other words, the sum of the squares residuals. So just kind of keep that in mind. You might think about that and ponder that fact as you go through here. The degrees of freedom reduced minus degrees of freedom in the full, which is in one of the denominators. Just remember it is just the number of predictor variables being considered for elimination. I think that's much easier than doing the subtraction, although you're free to do the subtraction if you want. So let's take a look at the partial F test. You do have to compute this by hand with the help of 2 regression computer outputs. And so a lot of the hard work is done for you. You just have to put in some numbers and divide. So what you need is the statistics from the regression model with all the predictor variables. That'll be called the full. And the statistics from the regression model with the dead weight predictors removed. That will be the reduced model. So let's just go through the theory. Regardless, whatever happens, the mean squared error full will roughly equal the error variance sigma squared. This comes from the variation of the data. Now, let's make some assumptions. If the null hypothesis is true, that is, our null hypothesis that the model can just be modeled by the reduced, the sum of squared error reduced measures the total variability of the data fitted. All right? And if that's true, then what that means is that the sum of squared error reduced minus sum of squared error full divided by degrees of freedom reduced minus degrees of freedom full will roughly equal the model's error invariance. What we're kind of doing here is saying this sort of mean squared error is also going to equal sigma squared. And that's kind of the idea. Well, if they're both equal to sigma squared, then we can compare the two. And what we'll do is we'll take the ratio like we did before with the other F test. So we're going to take the ratio, assuming the numerator is when the degrees of for when the null hypothesis is true, that is the reduced model is true, and then we're going to get roughly the same variance as divided by the mean squared error as a full. So the closer this ratio is to 1, the stronger the evidence for the null hypothesis that we only need the reduced model. the more this ratio is greater than 1, the more evidence for the alternative hypothesis, that is at least one of the dead weight predictors are needed. So that's kind of the theory. It kind of goes back to, again, this idea of variation, that we can estimate the overall variation of the model, making certain assumptions about whether the null hypotheses are true or not. So let's take an example at the blood-brain example. Over here on the left, I did the reduced model, and I just put in the 3 variables that I thought I needed, and I got out the output. And on the right, I did the full output. I put all 7 predictor variables in and got its sort of output in terms of the model summary. Notice that the reduced has an R-squared of 77.34%, and the full, because I put more predictors in, has a higher R-squared. Well, since it has a higher R-squared, this error should be less than, the sum of squares error is 3.446, will be less than the error of 37.802. So as one goes up, the other one goes down. So let's take a look at this. The sum of squared errors for the reduced model is 37.802, and the degrees of freedom is 30, as you can see there. And on the right side, the sum of squared error is 30.446, and you can find that in that part, and the degrees of freedom in the full is 26. Now, the 30 and 26, it just makes it easier for me that I threw out 4 predictor variables, so the degrees of freedom is going to be 4. The important phrase I'm going to need in the next slide is going to be 4. Oh, and by the way, I do need the mean squared error of the full. So I do need the 1.171, so I'm also going to need this. So in other words, I need 5 values from these 2 outputs from the linear regression models. So there's my formula again. My F test is above. And so just as before, I put my reduced minus the full, and then the degrees of freedom reduced minus the full, and then divided by the mean squared error is the full, 1.71. So if you want to stop the video and look back, or when you're looking at these PowerPoints, you can stop and look back where I got all these numbers. And if I put that all in, notice I changed this to the 4, just to remind me I was just getting rid of the 4 predictors. And I get 1.570. So now the question is, okay, that's my statistic. So what? Well, I need to make sure that whether this could happen by chance or not. So I need to calculate the p-value. So for the F statistic, I need both degrees of freedom for the numerator, and I need the degrees of freedom for the denominator. So it's good to keep this written down, because when we go to calculate this, we need to find this out. So you could actually use your calculator for this. I'm going to go ahead and use Minitab because I'm here. So the numerator degrees of freedom is the number of predictors eliminated. Hey, that was like our 30 minus 26, or 4. And the denominator is degrees of freedom for our sum of squared errors full, which I remember is 26. So let's go ahead and go to our Minitab. All right, so maybe I can blow this up a bit. Well, not what I need. So up here on top, I'm going to go to graph and the probability distribution plot. I want to view the probability, so I'm going to click probability, and then okay, I need to change this to the F distribution. Remember, we've got all these distributions like normal and t-distribution. I want the F. Fortunately, it's in alphabetical order. And then I need the degrees of freedom. The numerator is the number of predictors I got rid of, and degrees of the denominator is 26, which is degrees of error for the sum of squares of error. So I go ahead and hit OK. I then, well, actually I missed a step. I had this all set up, and so I was cheating a little bit. So I need to kind of do this again. So 4 and 26. Now I need to select the shaded area. Remember that my statistic that I got out was 1.57, so I need to put that in the x value because I know this and I need to find the probability. Remember, the p-value is a probability. And I find out that my p-value is 0.2119. And so when I calculate this, I get my degrees of freedom there, and I get my p-value of 0.2119, which I failed to reject. It's a little bit different than what you have in your book, maybe off by 0.1, but it's just due to some round-off error. If I would have put more into 1.57, more digits, I probably would have gotten a closer answer to what the book has. Now, so we failed to reject, so let's go ahead and write this out. And so the data do not give evidence that the predictor's lost tumor days or weight are needed above and beyond time treatment in female in the linear model to explain the log ratio. Again, it's nice to have your null hypothesis sitting around so you know what you're rejecting or failing to reject. One point here is that this is a case where we failed to reject but kept our model. So in some sense, we sort of accepted our null hypothesis. No, but officially we did not accept the model. We just do not have enough evidence for a better one at this moment. And we'll do some other things. And so it's not, when you're building your general linear model, you have to remember what is your purpose for it and how much can you accept. And so we're not saying, hey, this is the greatest model. This is a model that'll help us to predict and estimate. Okay? All right, so I will hope to do a couple more, one or two more examples in video 3. And hopefully you can keep your temperature down, or the appropriate amount, at 97.5, which sounds like an FM radio station around here. See ya.